Okay, so in this lecture, we will combine the material that we learned in the periods on the kernelized regressions together with SVM. I think these all pictures are very familiar with, and you guys, because you have seen these images before. Previously in the hard margin and soft margin, I only use the linear classifier, but in a lot of cases, maybe linear classifier is not good enough. You actually need to lift up your dimension into much higher dimensions. So this is very important. Once you lift up into much higher dimensions, the data could be linear separable. The most important thing is you need to find the right coordinate to work with. So this is the main idea, is we need to train our training data onto much higher dimension feature spaces with some mapping function phi from small d to big D. And this D could be really, really large. And in that cases, the data, will be separable in feature. And hopefully, data in the high space, as high dimension could be separable in the feature spaces. And then what you do is you train a linear SVM now to classify the data in the transformed feature spaces R big D. Then what you do is basically track and using like feature mapping phi to transform the new new data to classify it, and using the trained and the linear SVM model. But one of the issue is this D could be like so large, and this process to train like linear SVM could be very expensive. So that's why we are going to using kernel trick that we did previously. So let's do some math here. Okay, so the key here, so I want to emphasize here is I have some phi that is x to the and basically phi x, and basically in terms of dimension, this is R small d to R big D. Right? And the key is we want to learn a linear classifier. So fx, so basically with the feature of phi x dot w plus w0. Right, so this is like basically the new features that we have. So we call it feature map. So then as I want to go back to the soft margin and SVM, since this is like most reasonable one. So that means the objective is minimum W in R big D, W0 in R. So this is here we have a big D, and to indicate everything is in high dimensional right now. So it will be lambda summation I from 1 to the n, maximum of 0, 1 minus yi, fx of I, plus 1 over 2 norm of w squared. So this will be an objective or like loss functions. And the simplest cases that we think about is just phi x equal to x. This is go back to the linear classifier. So that means small d is equal to big D. So this is just nothing but the linear classifier. So another possible way that we have talked about this is the quadratic and the classifier. And for example, we can just using and the quadratic functions and to represent the feature, which is x squared to xd squared square root of 2x1 x2 to square root to xd minus 1 xd. So if you count how many dimensions that we have, this will just be simply by d times d plus 1 divided by 2. So and this phi could be like and a lot complicated. So I mean, and in that cases we have talked about I mean the kernelized regression that I mean this big D could be really large. Like in many cases, this D could be even bigger and bigger, like and significant bigger than n, the number of data that we have. Sometimes could be like, I mean, this D could be like positive infinities, which is the so the Gaussian kernels, so we have a talk about this. So, and basically that will be impossible to compute this fx, I mean, explicitly. So overall, it would be a really bad idea to solve this. I mean, so like solve this problem because this is too large to solve. Okay, so what I'm going to do is I'm going to change everything from and primal into dues, and hopefully, and the problem is, in terms of due formulation, that will be easier. So first things I'm going to do is I'm going to transform this objective into primal and formulations. So in primal and formulations, and what we have is basically, and we are going, and I want to remind you that, and the previous and formulation that we have, and is we have this Cassie things, right? So so what we do is we have a minimization of W in the R big D, and the W0 is in the R, and the Cassie is in Rn, 1/2 normal square, plus lambda of summation of I from 1 to the n of Cassie of I. Right, so this is subjected to, so we have yi, and so in this case we have phi x, which is so much more so we have features here. That is bigger or equal than 1 minus of Cassie of I. And the Cassie of I is bigger or equal than 0 for I is 1 to the n. So if, that's the training. In terms of prediction, so what we can do is so we know the solution of my W star. I think we have, and already showed that, this becomes a summation from I from 1 to the n of alpha I, yi, and phi of x of I. And then your y is going to be either +1 or -1, right? So this is +1 if summation I from 1 to the n of alpha I, y of I, phi of x of I transpose of phi of xi. Plus wait. So the new x here. So you have a new data. So prediction for new data x plus W0. If this quantity is bigger or equal than 0, this will be classified as 1. Otherwise, it will be classified as -1. Right, so this is the primal kind of formulation. So as I said, I mean, this is too expensive in terms of training, and too expensive in terms of prediction as well, because you actually need to explicitly write it out this phi of x right here, and you need to explicitly write out what is my W star. But as I mentioned, this W star will be very large. It will be in the dimension of big D. So it won't, I mean, it will not be ideal to explicitly write down so the situations that we have. Okay, so, and we also mentioned in the due formulation. So this is basically very similar, but the thing is we just changed the features from x into phi of x. So in terms of training, so this is training. And we change this and optimization, and it becomes the and my so my objective is with select variables and alpha right here. Okay, so this is minimization of my alpha in Rn, summation of I from 1 to the n of alpha I minus 1 over 2 double summation I from 1 to the n j from 1 to the n yi yj alpha I alpha j phi x of I transpose phi xj. Okay, so this is xi and xj right here, subject to summation I from 1 to the n of alpha I yi equal to 0. And alpha I is between 0 and pi for any I. So this is the training. And so you have seen this before. The only difference is right here is we have changed this into phi xi and phi xj instead of xi and xj. So then the prediction right here is basically we can and use what we already have right here. So we can and find out the W star, and also this and the W0. I think I missed the W0 right here. W0 star is yk subtract to 1 to the n of wi. So sorry, the n alpha I star phi of x of I transpose and the phi of xi so xk for any support vector k. Okay, so this is, and everything right here is the same. So, but you can see there are some very interesting things right here. In terms of training, this always shows up as a pair of phi xi transpose and phi xj. In terms of prediction, it also shows up as a pair of phi xi transpose and phi x, right? So in the due formulation, so in fact, what actually matters is is the this combination right here. So that's why we are going to using the same and a similar idea. We can define this kernel that this k of x of I and x of j, it's nothing but phi of x of I transpose and the phi of xj. And I'm going to denote this into as a matrix of ij. So in this case, it's this k, matrix is actually an n by n matrix. So this is particular ideal if for each entry of this is very easy to calculate, and my d is significantly bigger than n. So we have a talk about this in the the previous lectures, and we demonstrate there are certain kernels to calculate this phi xi transpose and phi j and phi xj for each entry is extremely cheap. And for example, you can choose the kernel function. You can define the kernel functions separately. That, for example, in terms of linear kernel, this just being x transpose of z. So, and this only takes about order of d. Second one, you can define, so this is a linear class and the linear kernel. Or what you can do is you can define the polynomial kernel, 1 plus of x transpose x and z power to the k for any k is bigger than 0. So this, and basically, and it's order of small d as well, but it contains phi, and it's equivalent to do is, my phi x is all the polynomial up to any degree of k. Right, so this is basically what is doing here. All right, so all the third one that we have is Gaussian kernel. So which is also a very common one. So you can define your phi, the k, x and z is exponential of minus x and z square 2 norm divided by 2 sigma square for sigma is bigger than 0. So this is basically a Gaussian kernel right here, and corresponding to phi as some infinite dimensional and feature spaces. So this is quite complicated, but turns out to be very useful as well. But you cannot choose k arbitrarily. That means this k has to satisfy certain Mercer condition, and we have a talk about this in the previous lectures as well. This Mercer condition states for all the data set from x1 to xn, this kernel matrix, if you plug in this x of I, xj, this k matrix has to be positive semi-definite, right? If it is, this matrix is not positive, semi-definite for all the data set. This is not a kernel. Okay. So if we allow this whole idea, so that means we can just simply replace this whole thing right here by k of x of I and x of j. Right here is being and replaced as k of x of I and x right here. So we could use this and the formulation of matrix to help us to solve this and this problem easily. Okay, so let's see how this and we actually implement everything from scratch. Okay, so see how this actually work. Go back to screen. Right here. So basically, here we're using SVM with the Gaussian kernel. In this cases, I'm adding an intercept as well, right? So basically, this is my and the prediction boundaries and the decision boundaries. So this is my decision boundaries. If we write everything in terms of alpha, and we know most of alpha I should be 0. For those alpha I is non-zero, this corresponding to the support vectors that we already talked about in the previous lectures. So here we are using some data is called XOR. So that means right here you can see we have a bunch of data, and this is being like -1 as a blue, and for the red that will be 1. So you can see this is -1 right here. This is 1 here. This is called XOR data set, and specifically for this data set, it is impossible to classify this data set with the linear classifier in a direct way. We can implement this with the soft margin SVM right here. So this is basically the same thing that we have talked about, and we're trying to solve these two problems with an SLSQP and a solver. Here we're trying to solve these two problems directly. Of course, you can solve with in the primal problems with hinge and with hinge laws we have a talk about. But the reason that we make decisions that to use this and do problem is I want to compare everything with kernel methods later on. All right, so this is, you have seen this code before, and we can make this decision and training with C equal to 1. So we have model soft, and we fit X train and the Y train. So right here you can see this is my classifier, which is very, very bad. You can see these are my support vectors, and this is my separators. So basically everything above is being classified with I believe is with with one color, and everything like in the middle will becomes so one color. So let me show like what is the result right here. So basically everything is being classified as a red, right? So you can see this is like, and most part will just be wrong, right? Because like nothing is being estimated as blue, and everything is being estimated as red. So basically you are getting like 50% of error, which is ridiculous in these cases, right? So okay, so and you can see this is my classifier right here, and everything will be classified as red. So, and this is very bad. And I mean, if you don't believe it, and you can make it to be like 10, and you can try to see what it can like improve. No. No, it's not working here. It's not. I mean, it's not finished. I see. This is still training here. Okay. I don't know why. I don't know why this is so slow. And let me rerun it. Okay, let's wait a little bit. Okay, so it takes a bit time. So so in my Colab, it takes about 4 minutes to run on the kernel and a kernel SVMs in a situation. So the differences here is actually you define, so what kind of kernel and the functions you are having right here. So I mean in this case, everything else is just being and very similar, because that's what we already defined. But the difference is here you have this kernels. So basically this like anagram like matrix and H is my phi here. So like phi and phi XX. So this will be just kernels and evaluate at x1 and x2 right here. And this is the vector of this gram matrix, and multiply this and the y and y transpose. So this is basically we're trying to formulate these two formulations right here. So you have a yi and a yj, but this is just being replaced by k of xi and a k of xj. All right, so so it's right here. So this is the fitting part, and everything else is just being the same. So this is being the same in SVM. This is being the same in SVM as well. In terms of predictions here, so this is differences here. I'm going to apply this and the kernels and the functions directly. As a function of so like new and the new new data of S right here. Right. So this is basically what we are trying to do here. So, and as a comparison of the soft margin SVM, you can see this is my x times y, and this is my gram matrix, which is xy times of xy transpose. But in this case, my gram matrix will be much more complicated. So that will be just being so and that will be just so my as hxx and the times of and the yp and the yp transpose. So this is basically the same like gram matrix that we have if we consider and vectorize everything of yi and the yj and the phi xi transpose and the phi j transpose. You just move this alpha I and alpha j out. So like everything like inside it, and this becomes your and your gram matrix. All right, so so this is basically the way you run for the SVM, but you can see this SVM runs quite a long time. It took like about 4 minutes to run. This is quite expensive in general, and we only have a couple hundred points. But if you have a lot of points, that will be a much longer time. But the benefit is if we're using the Gaussian kernel right here, so and the features and the space that we use is like infinite dimensional here. For this part, this intercept is not much relevant since we're already using this infinite dimension already. Whether adding this intercept or not will not make much differences. So this and it won't matter at all. All right. So and let's see. The general boundary that we have. You can see this is like quite impressive overall. It already learned some points that is like roughly it's like and hyperbolic functions and basically separate this like and a majority blues right here and these two regions right here will be considered as blue and everything like inside will be considered as a red. And you can rerun everything and to see different results that you are getting here. But in terms of confusion matrix, you can see we have and estimate everything blue correctly. I believe that's the testing data set. And sorry, and that's if we create the testing data set, that's my testing data set. And we can see everything being classified as blue is actually blue. Everything being classified as red, there are some like blue dots right here and scattered, so it makes some testing error. So basically, the testing error that we that we got is 10 and 10 out of and 10 so like 10 out of 200. So which is so like 90% of accuracy in this cases, which is quite significant compared to we use the soft margin right here. So this is basically almost every point is being classified wrong. Right, so this is really, really bad. So we are getting like only 50% of accuracy with the soft margins. On the other hand, and with a Gaussian kernel SVM, we're getting about 90% of accuracy on a testing data set. And by the way, we haven't do any like hyperparameter tuning. So if we tune the parameters, this, and then that will be expected, and this whole thing will be significantly improved. But of course, this is quite a difficult data set and to work with. But in general, if you are working with more realistic data set, if you find out the features is really a lot, and you want to lift the data into much higher dimensions, and you should think about it to using SVM if your data size is pretty small, couple hundreds, no more than 1,000, that would be like ideal to do this. But if you have a lot of data set, for example, 60,000 data set, then you should consider the trick that we did. You do some random feature projections and to project everything down into some manageable dimension, like couple thousands. Then you're using like and basically similar trick that we did in the Homo 1 question 3. Then sorry, I think Homo 1 question 2. Then you should get similar end result as the kernel SVMs. All right, so that's everything for the kernel SVMs. And of course, in practice, you probably were using scikit-learns. But the beauty of this and this course and also this lectures and tells you how to open the black box of the kernel SVMs and to tell you what is going on underneath of kernel SVMs and how they implement that. Why an SVM will be slow if your data and the number of data is large, but turns out SVM is independent with the dimensions of the data features. And you can have as large of the features if you want. It won't matter at all because it only depends on the number of n's right here. Right. So, and in fact, if you work with Gaussian kernels, it will have actually work out this, infinite dimensions and feature spaces, which is in practice you cannot even work with or handle with. But kernel SVMs can automatically solve this problem for you and very efficiently as well. And it can solve such complicated data set like XOR, which is a very typical data set to test highly and highly, as a highly nonlinear, and the data set cannot be separated by the linear separators or linear regressions. All right, so that's everything for this part. Okay.